तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we discussed the network functions associated with one port networks, the driving point impedance function and the driving point admittance function. Now, let us take the consideration of two port network which has got two terminal pairs. 1 and 1 prime are the terminals associated with port 1, 2 and 2 prime are the terminals associated with port 2. The conventional reference signs for the port voltages and currents are given in this manner. Port current I1 enters the network to the positive reference terminal for port 1 V1, and the port current I2 enters the network to the positive terminal having the positive reference sign for the voltage of port 2. This is the conventional way of taking these polarities of the voltages and currents. And the port concept ensures that if the current I1 enters the terminal 1, the same current must leave through terminal 1 prime, and likewise current entering terminal 2 must leave the network through terminal 2 prime. Now, we have 4 variables to deal with: V1, V2, I1 and I2. So, any two of these are linearly related to the other two by virtue of the linear time invariant property of the network. So, depending upon the particular occasion context, we take two of them as the excitation functions and the other two as the response functions. So, you have choice of taking any two as the excitation functions and the other as response functions, and depending upon the pair that you take as excitation functions, you get different types of parameters which describe this two port network. We will take up to start with a particular set of parameters called short circuit admittance parameters. Short circuit admittance parameters. This is one way of choosing two of as the input quantities and two as the response quantities. Here we treat I1 and I2 as the response quantities and V1 as V2 as the input quantities. So, I1 of S is linearly related to the two input quantities V1 and V2, and the proportionality constants for that are written as Y11 of S times V1 of S plus Y12 of S times V2 of S. So, the response in this, the response current I1 is linearly related to the input quantities V1 and V2 by the proportionality constants Y11 of S and Y12 of S. Similarly, I2 of S is Y21 of S times V1 of S plus Y22 of S times V2 of S. So, the network now is characterized by 4 parameters: Y11, Y12, Y21 and Y22. They are called the short circuit admittance parameters because dimensionally they are admittances, because the ratio of current to voltage, and these are the 4 parameters are called the short circuit admittance parameters. In matrix form, the same set can be written in a very convenient fashion: I1 of S, I2 of S is obtained as the Y11 of S, Y12 of S, Y21 of S, Y22 of S multiplied V1 of S and V2 of S. So, that is the convenient way in writing down the the parameters in matrix form relating the currents to the voltages. You observe that if I want to define y1 of s, if I want to find out what y11 of s is, I have to write y11 of s is the ratio of I1 of s to V1 of s when V2 is 0. Suppose I force V2 0 by short circuiting these two terminals and measure the current I1 of s in response to an excitation V1 of s, the ratio of I1 of s to V1 of s is y11 of s. Therefore, y11 of s is written as I1s by V1 of s when V2 is 0. That means you are short circuiting the output port 2 prime, this is 1 prime, and you are measuring this admittance at this point. You are connecting a voltage source V1 and measuring the current here. Now, let us see what is the y21 of s. y21 of s is the ratio of I2 to V1 when V2 is 0. Once again, in this equation, if you force V2 to 0, y21 of s is I2 of s over V1 of s. When V2 is 0. So, under the same excitation conditions, this current I2 to this V1 is your y21 of s. Now, suppose I want to find out y12 of s and y22 of s. So, y22, I will drop the functional notation s within brackets to simplify my writing. Y22 is I2 by V2 when V1 is 0. So, I2 by V2 when V1 is 0. That means the experiment that you suggested is, in this 2-port network you short circuit this and you apply a certain voltage V2 and measure I2, the ratio of these two is y22 of s. And in the same experiment, if you find out the ratio of I1 to V2, I1 to V2 when V1 is 0, when V1 is 0, I1 to V2 is y12. Therefore, y12 is the ratio of I1 to V2 when V1 is 0. That is under this experimental condition. So, you have these 4 individual parameters can be calculated or can be defined as the ratio of excitation to the Laplace transform of the excitation to the Laplace transform of response under these terminal conditions. Now, y11 and y22 are called driving point admittances. y11 and y22 are the driving point admittances because the response and the input are at the same location, associated the same terminal pair, either in the case of y11 or in the case of y22, I2 over V2. On the other hand, y12 and y21 are called the transfer admittances. Because the response location is different from the excitation location. Strictly, as I said, these are called driving point admittance functions, transfer admittance functions. But to simplify our referring to them, we simply refer to them as admittances, driving point admittances and transfer admittances. One thing you should notice is there is a particular order of the subscripts which is important. When you are calculating y21, it is I2 by V1. The first subscript refers to the response location. All our network functions are the response Laplace transform of the response to the Laplace transform of the excitation. The first subscript here refers to the response location, the second subscript to the excitation location, y21. Where a driving point function, both the response and excitation are at the same location, therefore, you have the same subscript y11. Similarly, y22. Look for y12, the response location is I1, port 1, the excitation is at port 2. So, I1 by V2 and this is y12. So, there is an order in the writing out these subscripts. The first subscript refers to the response location, the second subscript to the excitation location, and that is also in accordance with this matrix notation. The first subscript gives the row address, the second subscript the column address, and that is exactly what we have here also. So, there is some consistency in the writing down these equations, and that you should keep in mind when defining the other parameters. Another point to keep in mind is we use the lower case letters for these y's, not the capital letters, but the lower case letters. Small y and later on will be small z, because these are admittances defined under certain normalized conditions. The general admittances with other types of terminations can be used, we use capital letters, but when you are using specifically for short circuit conditions, they are called they use the lower case letters. Therefore, to be you must keep that in mind. y11, y12, y21 and y22 use small y's. Now, in all these definitions here, you observe that the natural form of the network is when the both ports are short circuit. You are introducing a voltage V1 here, and when this V1 is destroyed or deactivated or reduced to 0, this is a short circuit, and this is also a short circuit. Similarly, here you are finding the response of I1 and I2 when a voltage is introduced. So, when the voltage is removed or made equal to 0, both the ports are short circuited. So, these are the parameters measured under the short circuit conditions of the network. Both ports are short circuited. Therefore, they are called the short circuit admittance parameters. That is the reason why we call them short circuit admittance parameters, because we assume that the natural form of the network is like this, and you are introducing a voltage source here and measuring the responses. Similarly, you introduce a voltage source V2 and measuring the responses. So, the natural form of the network is both ports are short circuited, and therefore, the poles of all these network functions y11, y12, y21 and y22 turn out to be the natural frequencies of the two port network when both the ports are short circuited. And with minor exceptions here and there, which may come out as a result of the cancellation of common factors between numerator and denominators, except for that fact, all these functions will have the same denominator polynomial, because they represent the natural frequencies of the network under short circuit conditions. Therefore, when you calculate y11, y12, y21, y22, you will find that the denominator polynomial of all these functions is one and the same. It is only the numerator which may vary. Right. Now, how do we calculate this y11, y12, y21? For simple networks, you can use these definitions and find out y11, y12, y21 using these definitions. In a more general case, suppose I have a two port network here, you connect a voltage source V1, another voltage source V2 here, and you perform the loop analysis. So, through the network you have this loop current I1, through this you have loop current I2, and there may be internal loops here depending upon the structure of the network. So, you can write the loop equations for this network. You have say Z11, say there are m loops, Z21, Z2m, Zm1, Zmm. These are the loop equations, I1, I2, Im. As far as the forcing function is concerned, you have the sources only in these loops 1 and 2, because internally it is supposed to be a passive network, linear time invariant network, no independent sources are present. Therefore, you have V1 of S here and V2 of S here for the second loop, all the others are zeros. So, from this you can calculate I1 and I2 by taking the ratio of the appropriate determinants, and if you do that, you will get I1 equals V1 times delta 11 by delta m, where delta m is the mesh basis system determinant and delta 11 is the cofactor, plus V2 times delta 21 by delta m. That is, you replace the, when you are calculating I1, you replace that in the first column by this column V1, V2 and zeros. Therefore, when you expand that, you will get this. And similarly, I2 will be V2 V1 times delta 1 2 by delta m and V2 times delta 2 2 by delta m. So, it is clear that this will give me y11 and this will give me y12, this will give me y21 and this will give me y23. So, you can calculate, you can write down the loop equations for the network in terms of generalized impedances and calculate the ratio, the appropriate cofactor to the mesh basis system determinant, and that will give you y11, y12, y21 and y22 in a general case. I mentioned earlier that out of these 4 quantities V1, V2 and I1 and I2, we can take any 2 as the excitation quantities and take the other 2 as responses. Let us now consider that the currents are excitations and the voltages are the responses. Therefore, I can write V1 of S as an impedance Z11 of S multiplied by I1 of S plus another impedance Z12 of S multiplied by I2 of S, and similarly the second voltage is Z21 of S times I1 of S plus Z22 of S times I2 of S. Now, we now have the voltages as the response quantities and the currents as the inputs. That means essentially what we are thinking of is a network with 2 current excitations I2, I1 and V1 and V2 are the response quantities. So, these are called open circuit impedance parameters. For example, if I want to measure Z11, all I have to do is Z11 is the ratio of V1 to I1 when I2 is 0, V1 to I1 when I2 is 0. Similarly, Z21 is V1 V2 by I1 when I2 is 0. That means you are now thinking of a situation where a current I1 is led in and you are measuring out the responses V1 and V2. The ratio of V2 to I1 is Z21, the ratio of V1 to I1 is Z11. So, naturally you get a similar set of defining relations for Z12 and Z21. For Z1 and Z12 and Z22 to find out, you have to make I1 0. Therefore, if you make I1 0 and introduce a current I2 here, and this is the response V2 and this is the response V1, Z12 is V1 divided by I2 when I1 is 0, and Z22 is V2 divided by I2 when I1 is 0. So, these definitions are completely in parallel with the defining relationship for the Y parameters, except now the currents are the excitation sources, and therefore, we also observe that if this current I1 is made equal to 0, both the terminals are open. Similarly, when I2 is made equal to 0, they are both open. That means these are network functions whose poles represent the natural frequencies of the network when both the ports are open circuited. So, the raw form of the network is that this is both the terminals are open and you connect a current source, the soldering type of entry for the 2 currents and finding out the responses. Whereas, in the short circuit parameters, the raw natural form is the short circuited and you are introducing a voltage source in that, the Pliers type of entry as a voltage source. So, we have these are called open circuit impedance parameters, and naturally Z11 and Z22 are the driving point impedances, because V1, I1, V2, I2 are individually measured at the same pair of terminals. So, Z11 and Z22 are the open circuit driving point impedance functions, Z12 and Z21 are the open circuit transfer impedance functions. So, to summarize, the Z parameters represent the network functions defined under open circuit conditions by introducing current sources. When the current sources are removed, then the two ports are open circuited. There the poles of all these network functions represent the natural frequencies of the network under open circuit conditions. Z11 and Z22 are the driving point impedance functions. Z21 and Z12 are the transfer impedance functions, and we can define them in this fashion individually. And in order to find out these parameters for a general network, we can do the loop current in the node voltage method of analysis. You can introduce a current source here, take this as the datum node, find out the response for V1 and V2, and then you can perform the node analysis and get these values of Z11, Z21, Z12 and Z22 in more or less similar fashion as what we have demonstrated for the case of admittance functions. So, let me write this table here. In this table, we have already discussed, given the matrix relation for short circuit admittance parameters are called Y parameters. In a similar fashion, we can write V1 of S and V2 of S as Z11 of S, Z12 of S, Z21 of S, Z22 of S times I1 of S, I2 of S. These are called open circuit impedance parameters. Again, Z11 and Z22 are the driving point impedance functions. Open circuit driving point impedance functions, whereas Z21 and Z12 are the transfer impedance functions. Now, looking at these two, after all, you have a matrix relation. The currents are given in terms of voltages. So, voltages, suppose from this you want to express voltages in terms of currents, you have to invert this matrix and write V1 V2 is this matrix inverse times I1 I2. So, one can expect that this entire matrix here is the inverse of this matrix. So, the inverse of this matrix is this, the inverse of this matrix is this. So, Z and Y matrices are inverses of each other. That does not mean that Y11 is the inverse of Z11. Look at the definition of Y11. How do you find Y11 is the ratio of I1 to V1 when V2 is 0. So, you short circuit this and measure this admittance, that is Y11 of S. How do you define Z11? It is the ratio of V1 to I1 when I2 is 0. So, you are keeping this open circuited and measuring this impedance, that is Z11 of S. So, the network in which this admittance is measured and the network in which this impedance is measured are different. This n other terminals are short circuited, here the two terminals are kept open circuited. Because of this reason, Z11 is not necessarily equal to 1 over Y1. So, the short circuit driving point admittance at port 1 is not the reciprocal of the open circuit driving point impedance at port 1. These two are not reciprocally related, but this entire matrix is the inverse of this matrix. So, you can show that Z11 is related to all the Y parameters in some fashion. We can invert the matrix and find out, but individually Y11 is not equal to 1 over Z11 because the two networks are different. Now, apart from these two basic matrices. You have various other types of matrices which I would like to talk about now. You can express V1 and I2 in terms of I1 and V2. So it will be H11, H12, H21, H22 times I1 and V2. Again, I am dropping the functional notation for convenience. You can also express I1 and V2 in terms of V1 and I2. Normally, these are referred to as G11, G12, G21, and G2. These are called hybrid parameters, or H parameters or hybrid parameters. Commonly used in transistor work. The reason why they are called hybrid, they are mixed variables, because you are not talking about both the input quantities as a voltage or currents. One is a current, the other is a voltage. The response also, one is a voltage, the other is a current. Therefore, they are mixed variables. They are called hybrid parameters. These are called inverse hybrid parameters. H parameters are inverse H parameters. And once again, you can define example. If I want to find out what G21 is V2 over V1 when I2 is 0. Because V2 is G21 V1 plus G22 I2. Therefore, when make I2 equal to 0, V2 equals G21 times V1. So, like this, you should be able to define each one of these parameters with the appropriate terminal conditions. Now, you observe that this is the ratio of the response when I2 is 0 and you are measuring the V2 over with a particular excitation. So, in defining these G parameters, this is the pattern of excitation and response that you are having. So, the natural form of the network is when V1 is 0, this port is short circuited, the other port is open. So, in these hybrid parameters, it turns out that one port is open circuited, the other is short circuited. Therefore, the poles here represent the natural frequencies when one port is open circuited, the other is short circuited. Whereas, here both the ports are short circuited. This is the case where both ports are open circuited. In the case of hybrid parameters, one of the ports will be open circuited, the other is short circuited, and the natural frequencies under those conditions will be the poles of the appropriate network functions here. In addition, you also have another important category of parameters which go by the name transmission parameters. Also called ABCD parameters, sometimes called chain parameters. Here, assume that this is a transmission line and you are talking about the output of the transmission line. This current is minus I2 because we are defining the port current I2 as leading inwards. Therefore, 2 prime, this is the voltage and the current that is being fed from at the output end, and the receiving end here of the transmission line, let us say V1 and I1 are the voltage and current. So, we can think of V1 and I1 are the quantities at the sending end, and V2 and I2 are the quantities at the receiving end, like a transmission line. The current is going out of the transmission line. This is the terminal voltage at the receiving end, the terminal voltage and the current at the sending end. So, if we express V1 and I1 in terms of the receiving end quantities V2 and minus I2, then these are related by parameters A, B, C, D. Again, A, B, C, D are functions of S in a general case, and this is called the ABCD parameters. So, that is how these are defined. Now, let us see how do you find out C. C is the ratio of I1 to V2 when I2 is 0. So, I2 is 0 this is kept open circuited, and is the ratio of V2 to I1 to V2. So, the ratio of V2 CV2 is I1 equals CV2 where I2 is 0. I1 equals CV2 when I2 is 0. So, normally when you define any network function, you write C equals I1 by V2. You can think of V2 as an excitation, but unfortunately here I2 is forced to be 0. Therefore, you can't think of connecting a voltage source here and again make sure that I2 is 0. Therefore, you have to think of a current source here I1, that is the input, and you are measuring the V2. Therefore, V2 by I1, the response to the input V2 by I1 turns out to be therefore 1 over C. So, in the case of this chain parameters, these ABCD values do not turn out to be the network functions in our standard format in the ratio of the Laplace transform of the response to the Laplace transform of the input. It turns out that in this particular case of the chain parameters, the reciprocals of these quantities ABCD 1 over C, 1 over A, 1 over B, 1 over T turn out to be the network functions in our conventional sense of the Laplace transform of the response to the Laplace transform of the input, because C normally would assume to be I1 by V2 and V2 being the response, but if V2 is the input, if the V2 is the input, we can't force current also to be 0, because you can't connect a voltage source here and then demand that current I2 is 0. So, it turns out that as far as the ABCD parameters are concerned, it is the reciprocals of the ABCDs which are the conventional network functions, but we use this ABCD also in network functions in this relationship, but they deviate from our standard definition of a network function. Now, in all these cases, that means we have essentially 5 important sets of parameters. Actually, you can have a 6th also. We can express V2 and I2 in terms of V1 and I1, that is the inverse of this matrix, that becomes 6. After all, we have 4 quantities here, V1, V2 and I1, I2. You can select a pair of 2 quantities from 4 in 6 different ways. So, you have 1, 2, 3, 4, 5, and if you take the inverse of this, you get a 6th set of parameters. But normally that is not done, that is not very important. These are the 5 sets of parameters which are important: the short circuit impedance matrices, the open circuit impedance matrices, the hybrid parameters, the inverse hybrid parameters, and the chain parameters. The importance of the chain why we call the chain parameters, it will be brought out later. And in the both Y matrix, Z matrix, H matrix and G matrix, we use the lowercase letters because they are under standardized termination conditions. It is conventional to use the lowercase letters. As for the ABCD parameters are concerned, it is conventional to write them by capital letters A, B, C and D. It is also important for us to recognize the dimensions of each one of these quantities. As far as Y and Z are concerned, their impedance and admittance is no problem at all. H11 has the dimensions of resistance or impedance, because V1, H11 is V1 divided by I1 when V2 is 0. Therefore, this has the dimension of impedance. H12, V1 divided by V2 when I1 is 0, that has is a dimensionless, is a ratio. Likewise, this is a ratio. This has the dimensions of an admittance. Similarly, G11 has the dimensions of an admittance. G12 has the dimensions as a ratio, no dimension at all. G21 is dimensionless. G22 has the dimension of an impedance. Likewise, you can associate the dimensions with each one of these. So, the important thing is for us, we must have the familiarity with these, but we must be able to define each one of these parameters in any one of these sets like in this fashion. We must know the dimensions of the quantities that are involved. And furthermore, by manipulating these equations, if somebody gives us the admittance parameters of a 1-port, 2-port network, from these Y parameters you should be able to derive any other set of parameters. After all, from this you have to write down 2 equations for I1 and I2 in terms of V1 and V2, and using those 2 equations you can manipulate these equations to express I1 V2 in terms of V1 I2 by manipulating these equations. Therefore, in other words, given Y parameters, we should be able to get G parameters as a 2-port network. Given Y parameters, should be able to get H parameters, and so on and so forth. So, you should be able to manipulate these equations and find out one set of parameters from any given set, and that is straightforward. It is not very difficult. I mean, tables are set up, it is available in textbooks, but we do not have to always use these tables. We should be able to deduce one set of parameters from the other by manipulating these equations. One or two examples will work out a little later. So, at this point of time, let us now look at these, let us take one or two examples to illustrate these ideas which we discussed just now, that is to derive one set of parameters from the other set, and then we will try to work out some other examples using these various parameters. Let us now take an example, express h parameters in terms of y parameters. Suppose there is a question that is asked. You recall that h parameters have this form h11 I1 plus h12 V2 and I2 equals h21 I1 plus h22 V2. But y parameters have the form I1 equals y11 V1 plus y12 V2 and I2 have the form y21 V1 plus y22 V2. So, now we have to express V1 and I1 in terms of I1 and V2. Therefore, we have to find out from this V1 equals from this I1 by y11, V1 equals I1 by y11 minus y12 by y11 V2. That is what we are having, I1 by y11 minus y12 by y11 V2. So, that means that particular equation is in accordance with this form. So, we already have h11 h12. As far as I2 is concerned, we express I2 in terms of I1 and V2, but we have I2 expressed in terms of V1 and V2, but V1 expression we already know. So, substitute this here. So, you get I2 equals y21 times, for V1 we substitute this expression I1 divided by y11 minus y12 by y11 times V2 plus y22 V2. So, we have now expressed I2 in terms of I1 and V2. That means, this will be y21 divided by y11 times I1 plus y22, this is coming from this y12 y21 divided by y11 times. So, we have expressed V1 and I2 in terms of I1 and V2. So, from this we can readily see that h11 is 1 over y11, h12 here minus y12 over y11, h21 equals y21 over y11 and h22 is this quantity y22 minus y12 y21 divided by y1. That is what we are having. So, this you can write this, if you have a common denominator, this is delta y divided by y11, where delta y is the determinant of the y matrix y11 y22 minus y12 y21. That is, you have the y matrix is this y11 y12 y21 y22. So, if you take the determinant of that matrix, this will be y11 y22 minus y12 y21, and that is what we are having as delta y by y1. So, in this way you should be able to convert one set of parameters into any other. We shall now consider some restrictions imposed on these parameters by a network which is called a reciprocal network. A reciprocal network is a network which satisfies reciprocity theorem. What is reciprocity theorem? Reciprocity theorem states is, in a linear network containing bilateral two terminal elements and reciprocal two terminal pair elements, the ratio of transforms of response means either voltage or current and ratio of transforms of response and excitation. There is excitation may be current or voltage. The ratio of the transforms remains unchanged or remains the same if the locations of response and excitation are interchanged. If the locations of response and excitation are interchanged. First of all, let us see what this means. We are talking about a linear network containing two terminal elements, bilateral two terminal elements. That means the ratio of voltage to current, the form of the relationship remains the same whether the current is in one direction or the other. All our RLC elements are bilateral two terminal elements. Reciprocal two terminal pair elements, that means you have two terminal pairs, your mutual inductance M12 is the same as M21. So, there are such the elements are called reciprocal two terminal elements. So, if you have RLCM elements, the ratio of transforms to response to excitation will remain the same if the locations are interchanged. That means, let us take an example. Suppose I have a network like this. Suppose I put a voltage source Vi here and measure the current here, Ij. So, I am finding out the current here in response to an excitation introduced here. So, I get Ij of S over Vi of S. So, let us say this is one particular transfer ratio, transfer function T1 of S. Now, if I interchange, that means I am measuring the current here by introducing a voltage source here. Suppose I reverse this, I introduce a voltage here, say Vk of S, and then I measure the response here, IL of S. So, now where I had originally the excitation point, I am finding out the response, and where I was earlier measuring the response, I am introducing the voltage. So, IL of S divided by Vk of S, let us say is T2 of S. So, this is another transfer function. The reciprocity theorem tells us that these two ratios are the same because the response ratio, the ratio of response to excitation remains the same when their locations are interchanged. In doing this, we must be careful that this current is entering the dot point as far as the source is concerned. This current is also entering the dot point as far as the this source is concerned. So, you must have some consistency in the symmetry in the reference size, that is important. And secondly, I purposely write response voltage current here and reverse the order here. So, when you are measuring the ratio of response to excitation, you must take the response. If it is voltage, the excitation is the current. If the response is current, the response excitation is the voltage. It does not work out when both the responses are voltage, both the response and excitation are voltages, both the response and the excitation are currents. We will illustrate that a little later, why it is so. So, one must be a current, the other must be a voltage, that is important. And any network which satisfies this is called a reciprocal network. So, a reciprocity theorem is applicable to the types of networks which contain these elements. So, we should also be familiar what types of elements will not have reciprocity theorem satisfied. If you have linear dependent sources, control sources and so on, it does not satisfy reciprocity theorem. So, the types of networks, another element which some of you may be familiar with, what is called a gyrator, is an anti-reciprocal two terminal pair element, that also it will not satisfy reciprocity theorem. So, reciprocity theorem is valid essentially for RLC networks with mutual inductances also present. As an offshoot of this, what we have here is, suppose I have a 2-port network, and let us say this is the raw form of the network, this is a basic network. If I introduce a voltage source here, V1, and measure the current here, I2. So, this is I2 by V1 when V2 is 0. This we call this is Y21 of S, we know that. Now, in this raw form of the network, suppose I introduce a voltage here, V2, and measure the current response here, I. Then I1 by V2 is Y12 of S. This is what when V1 is 0. This is how we define this. So, if this is a reciprocal network, Y12 must be the same as Y21. So, if this is a reciprocal network, it satisfies the reciprocity theorem, Y12 is equal to Y21. Similarly, it can be shown that for a reciprocal network, that means if the 2-port is reciprocal, of course, we know that Y12 is equal to Y21. Similarly, it can be shown that Z21 is equal to Z12, and it can be shown that H12 equals minus H21. Again, H12 and H21 can be expressed in terms of Z parameters, and this can be shown. And similarly, AD minus BC for a reciprocal network is equal to 1. This comes from the fact that 1 over C happens to be Z21, and Z12 happens to be AD by C minus B. So, that means AD minus BC by C. This is AD minus BC by C. So, for a reciprocal network, these two must be equal, therefore, AD minus BC is equal to 1. So, this is the consequence of reciprocity as far as the parameters are concerned. So, in this lecture, we have introduced ourselves to the various sets of parameters characterizing a 2-port network. These are the Z parameters, the Y parameters, the hybrid parameters H, the inverse hybrid parameters G parameters, and the transmission parameters ABCD parameters. We saw that these are independent specifications. One set of specifications can be obtained from the other. We should be able to convert one set of parameters into any one of the other required sets. And we also saw an example where such a transformation can be done. Next, we consider the case of a reciprocal 2-port network, which basically consists of RLC-M elements. In such cases, we have additional constraints on the parameters in any individual set. Basically, the Z parameter, the two transfer impedances must be the same. In the case of short circuit admittance parameters, the two transfer admittances must be the same. In the hybrid parameters, H12 must be equal to minus H21, and in the case of ABCD parameters, AD minus BC equals 1. That means the determinant of the ABCD matrix must be equal to 1. These are all equivalent conditions. We will study some additional properties of these parameters, and then how for particular configurations one set of parameters is easier to calculate than the others. All these questions will be taken up in the next lecture.